is also in Trivandrum.
I said it's a bit remote, right? I said Trivandrum.
Yeah. That place is little remote. Every day I have to travel, but still.
Okay, so we will start. It's time. So good morning, good afternoon, good evening, good night for all our friends and colleagues all over the world. Welcome to our seminar series or webinar series on critical transitions in complex systems. The seminar series is jointly hosted by IIT Madras in India and Potsdam Institute for Climate Impact Research. This webinar series brings together experts from varying fields such as climate science, optics. Today we have optics, neuroscience, fluid mechanics, and combustion, and aims to disseminate the state of the art in predicting critical transitions in these diverse fields of study. The seminar series takes place every month on the last Monday of every month. So please mark your calendars. So this is the last one of this year. We'll have the next one in January. Before I invite Jürgen to introduce the speaker, a few housekeeping notes. And please use the question and answer or Q&A box to ask the speaker your questions. Just type the question in there and the speaker will answer these questions. At the end, we will have ample time. So now I request Jürgen Kurz to introduce Raj. I have just put up a slide on him, but you can go ahead, Jürgen.
Okay, I'm very happy to introduce today and to welcome today Professor Rajarshi Roy. I think you all know him. He is director of the Institute for Physical Sciences and Technology at the University of Maryland. Got his PhD in Rochester, is fellow of APS, of Optical Society of America, and many other things. But this is important, of course, but much more important is his work, his scientific work. And he is really bridging very, very successfully nonlinear optics and nonlinear dynamics, complex system science. I looked a bit into the history. He found already stochastic resonance for the first time in laser systems in 1988, also a few years back. Then also synchronization in the early 90s, then optical communication, all experimental, but with strong theoretical background, all in the last century. But then he went over more to complex networks, made observations of chimera phenomena in also laser systems, but also looked much far away from this. For instance, studies on cortical networks with real hard neuroscientists, published several important papers. And of course, I could mention several other things, time delay couplings, and also more recently, no, I think not only recently, but in waves here is now again with the topic of random number generators. I remember when I visited him first time many years ago, he told me already about this, but then he found new principles. And I'm really very happy that he will give a little insight into his great work. Raj, please, you have the floor.
Thank you so much. Shall I try to share the slides?
Yes, please.
Yes, please.
Okay, so let me see if I can share screen.
Yeah, the green button could be.
Yes, yes. And can you see the screen now?
You need to make it full.
Yes.
Slideshow. Yes. And is this the right way to share it?
No,
can you see?
No, this is showing that your view.
This
do the other thing, whatever you did earlier.
This go back. I will go back. Yes.
Yeah. This was the same thing that happened first when you tried, and then you changed it.
And does this work now?
Still shows the same like present view.
Professor Roy, you used a display settings option on the top.
Yeah. Yeah, you clicked on the display setting and changed it. So that's how it became fully. Now you have got mute actually. Professor Roy, you're muted, unfortunately. I cannot hear anything. Can you hear, Ankit?
No, we cannot hear you now.
I cannot hear anything.
We cannot hear you, Raj.
Totally not. Possible.
We are unable to. We don't hear you.
Professor Roy, can you restart the talk?
Yeah.
I think that will solve everything.
Yeah. Can you just quit and come back? I think that would be better because everything got tried out and everything worked.
Okay. Yes, I will quit and come back.
Now it
Okay.
has come back. Now it's fine.
You're audible now.
Now you are audible. Yeah.
Okay. I will try to share the right screen now
Right. Yeah.
and try it again.
Yeah. Now you make it.
So let's see.
You last time you made it slideshow and then clicked some display setting.
Yes. So I tried to,
The top you had the display settings.
yes. And let me,
Just after the taskbar on the top.
yes, yes, yes. I will try to swap it.
Yeah, perfect.
Now I have to turn off the subtitles, which I will do.
Now it's very good. Raj, it's
Okay, good. And I have to turn on the sound.
Yeah, right.
I have to share the sound so that the sound on the video clips works. Okay. Okay. So now we're ready to start, I hope.
Yeah.
Thank you so much, Professors Sujit and Professor Kurtz, for this invitation, which was totally unexpected. And I was delighted to try to figure out what I should present to all of you who are, many of you are experts in the field, originators of many research topics in the field. And I'm sure that there are some who are starting to enter the field right now. So I hope that both sets of people or multiple groups of people will find something of interest. But the topic that I tried to use to talk about is complex photonic dynamics. And starting with counting single photons, talk a little bit about communication with light and chaotic systems, and then generating random numbers. And finally, I will try to end with showing a critical transition from Poisson statistics and stochastic processes over to chaotic attractors, if I can. So that's my goal, and I'm delighted to be here, and I will try to answer the questions that come on the chat, I believe, at the end of the presentation. But here's a picture of a critical transition that occurs at the beginning of a baby's life. A baby is born and begins to see the light. And what is plotted over here are the sleep and wake periods of a baby. So the light parts are corresponding to, can you see my pointer over here?
Yes, we can.
Yes, you can. So you see totally random times of waking and sleeping are going on, and the parents are probably having a hard time. But as time progresses and the weeks go by, you can start to see a pattern emerge of synchronization of a baby's sleeping and waking times with the cycles of the daylight and night that occur. And this is data taken a long time ago, around the year of my birth, 1954. I believe that's when this 53 is when this was originally published. So this is one of the most interesting transitions to entrainment or synchronization with the circadian rhythms of the baby with the daylight and night. Now, in India, since this is a seminar that is somehow bridging India and Germany, I thought I should start with this slide where we talk about what happens to a baby when it grows up. And when babies grow up, they often have difficulties with vision. As we get older, this becomes more and more prevalent. And the Indian surgeon, Shushruta, wrote a book in Sanskrit around 800 BC, which describes 76 ocular diseases and ophthalmological surgical instruments and techniques. And he has been described as the first cataract surgeon. So optics and the optics of vision particularly were an important topic of discussion at that time. And you can see that later on, Alhazen had the idea that light is responsible for vision. It's not something coming out of the eye, but the eye is receiving reflected light, and we begin to see objects as a result of that. And he wrote this book called Kitab al-Manazir, Book of Optics. So to connect to Germany is very easy because Hermann von Helmholtz in the 1800s was one of the great pioneers and teachers of the foundations of vision and hearing. And his students numbered many. Some of them were people whose names you will recognize right away. And I will say a little bit more about some of his students, but I always think of him as one of the great pioneers of all science, and energy conservation in particular was one of the areas that he was very interested in. But here I want to focus more on his studies of the eye. Now you see a picture of the eye with cutouts and blow-ups over here showing the incidence of the eye and the retina, which is at the back. So different components function beautifully together to actually create the signals, which are electrical signals that are carried by the optic nerve from the eye to the brain. And this is how we see different objects and different things, and how I'm seeing my picture on the screen right now. So Helmholtz was very interested in trying to look at the eye, and not just at the eyes from corpses or cadavers, but he was curious as how to do this. And so for his lectures, he created a beautiful instrument. And this is the ophthalmoscope. The Helmholtz ophthalmoscope was something he created for his students, and basically used very simple ways of collecting signals from a light source that was imaged onto the subject's eye by using a mirror, and then a lens was used by the examiner to look at the part of the eye that was the retina at the back of the eye. So this is a very interesting device that he made, that he invented, which is still used today after almost 200 years in pretty much the same configuration and the same arrangement that Helmholtz invented. Now, when one looks with the Helmholtz ophthalmoscope at the retina, this is what one sees over here. And if you look at this picture on this right, you can see that the single lens of the eye actually inverts the image, but the brain gets used to this inverted image, and we see things upright as our brain compensates for this inversion, and we see images in the right orientation. There's a complicated set of biological, chemical, and biochemical and electrical impulses finally result from this whole chain of functional activity in the eye, and the brain eventually gets an electrical impulse that one sees. Okay, so this is a very non-trivial way in which the human eye is actually able to see light. Electromagnetic waves, which is what light is, was something that Helmholtz really wanted his student Heinrich Hertz to discover. And he encouraged Hertz to start experiments on this. So as you can see, Hertz became a full professor at the University of Karlsruhe. And then he began his experiments and discovered electromagnetic waves and passed away at the age of 36, shortly after that. But he said that when asked, what is the use of your experiments? He said, it's of no use. This is just an experiment that proves Maestro Maxwell was right. We have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there. And asked about the ramifications or the applications of his discoveries, Hertz replied, nothing, I guess. So this is a very beautiful example of curiosity-motivated discovery, and that has led to enormous impact on all of humankind. Now, the electromagnetic spectrum, which Hertz began to investigate, is now known to spread over how many orders of magnitude is this? This is literally, many orders of magnitude that are covered in wavelengths or frequencies of electromagnetic waves. And the visible part of the spectrum is tiny. It's just this narrow little slot over here, which has all the colors that we actually see with the human eye, using 3 different kinds of receptors that are sensitive in the 3 different color levels. So our human eye is able to look at these different kinds of color schemes thanks to the light from the sun that comes to the earth. And as you can see, the atmosphere doesn't allow all kinds of light or electromagnetic radiation to come through to the earth, but here is a channel in the spectrum which can appear on the Earth's surface from the sun. And this is the basis of vision as we know it. So to bring together our communities from India and Germany together, I wanted to introduce J.C. Bose. As German physicist Heinrich Hertz started to reveal electromagnetic waves in free space, Bose started to follow up microwave research in Calcutta, India, and ultimately succeeded in reducing the wavelength to the millimeter level. And in 1895, in a public demonstration, he ignited gunpowder and rang a bell at a distance using millimeter range microwaves. Okay, and he wrote an essay titled Adrishya Alok, which means invisible light at that point, because of course these microwaves at the wavelengths that he was working at could not be visually seen. And J.C. Bose lived from 1858 to 1937. And he went to England thinking that he would study medicine, but the smells in the hospital were very difficult for him. So he actually ended up moving to Cambridge for an education. And once he got his degrees there, he returned to India in 1885. And he was encouraged enormously by his teachers. Lord Raleigh and Francis Darwin were his teachers in physics and botany. And these were the areas of research that J.C. Bose followed throughout his life. So what is interesting to look at is that in the 1890s, J.C. Bose was involved in microwave research, basically. And in 100 years ago, this is an article written in 1997, J.C. Bose described in the Royal Institution in Great Britain the experiments that he had been doing. And he used waveguides, horn antennas, dielectric lenses, various polarizers, and even semiconductors at frequencies as high as 60 gigahertz. So he was really working with materials and with detectors of radiation that people didn't even have the word semiconductor at that time. And he was actually experimenting with those things. And here's an early patent from 1904 from the United States Patent Office that was made out to Jagadish Chandra Bose of Calcutta, India, and to Sarah Chapman Bull of Cambridge, Massachusetts. She was instrumental in actually getting this patent issued, and she was a disciple and a devotee of Swami Vivekananda that some of us from India are intimately familiar with. So a detector for electrical disturbances from 1904, the United States Patent Office. And here's a picture that shows what Bose's detector actually looked like. It's shaped in the form of an eye, as you can see, which is kind of curious, but the instrument that is really responsible for seeing or detecting electrical disturbance is a semiconductor. And it's a lead sulfide crystal, galena crystal, that he utilized with a point contact. And this was a very unique discovery of use of a semiconductor as a photoresistor. When light fell on it, its resistance changed, and Bose made use of this for detecting light or electromagnetic radiation across a wide range of wavelengths. This is the galena detector. And he called it an artificial retina because with a suitable arrangement, it could be used as a radiometer or measurement device for electromagnetic radiation. And this was well ahead of time in a certain sense. Shortly after Bose's patent, here is a patent from 1906 by Picard that introduced another very important technology, and this was a silicon crystal detector. So here's a silicon crystal right here with a point contact, and means for receiving intelligence communicated by electromagnetic waves. Patented 1906, November 20, just around this time of the year. So a very fascinating history. Marconi in Italy was also fascinated by these discoveries, and in 1895 he began experiments at his father's country estate, and he succeeded in sending wireless signals over a distance of 1.5 miles. So simultaneously with Bose and others, he was fascinated by electromagnetic radiation, but he didn't stop with 1.5 miles. He really wanted to cross the Atlantic with radio waves. And here is a little video clip. I hope it plays.
Crude-looking instrument, but one that was destined to develop the modern miracles of radio. Marconi amazed the world by sending and receiving wireless messages 3,000 miles across the Atlantic. Since its invention, wireless has saved numberless ships and human lives from ocean disaster. Mankind can never forget its debt to Guglielmo Marconi.
Okay, so I hope you could hear the video sound and watch Marconi doing his demonstration. And this was also a tragic incident took place in 1912, shortly after Marconi introduced all this, and that was the sinking of the Titanic. And it was radio signals that allowed locating the wreck of the Titanic and the rescue of some of the passengers from that ship. But now the idea of the artificial retina that Bose had titled his detector comes back to us in a modern form. And this is Mark Humayun, who is a scientist in the US. And Mark Humayun is an ophthalmologist and biomedical engineer and an immigrant from Pakistan. And he created this system of trying to restore sight to certain patients who had lost it because of problems with retinal disease and so on. And it's called the Argus 2, and he created this artificial retina. I will not play the video in this case, but it's a fascinating modern development of semiconductor detectors coming back to benefit humankind. Now, can the eye see a single photon? We know that the eye is a very sensitive detector of light. And the first study of this particular question was published around 1942 by Hecht, Schler, and Piren, and working with retina from a frog to actually do these experiments. And they thought that pretty much very small numbers of quanta of light, photons of light, could be detected by the retina. And here is a follow-up in 2016, more modern version of this, direct detection of a single photon by human eye. And this is something that I was reading with a lot of interest recently. Now, coming to more modern topics and books, here's a couple of topics that I wanted to introduce, coherence and randomness. And I was introduced to these topics from my two teachers at the University of Rochester, Emil Wolf, from whom I took my first course in stochastic processes, and Leonard Mendel, who became my thesis advisor. And this is Emil Wolf's book, as he called it, my book with Max Born. And he wrote an updated version of Max Born's Optique in 1959, I think it was when it was first published. It has been cited many times, as you can see. And then Wolf and Mendel worked together. They were very close friends with offices side by side, and they collaborated for over many, many years, I think over 40 years. And they wrote this book, Optical Coherence and Quantum Optics. And this book was in the process of being written when I was a graduate student at the University of Rochester. And many of us students had to read different chapters and look at the topics treated there and so on. And it was a wonderful learning experience for us. So it was something that introduced me to optics and totally transformed my wish to become a particle physicist. That got sidetracked, and I decided that I was going to try and learn experimental optics. And requested Professor Mandel to take me on as a graduate student. And he said, have you ever done any experiments? And I said, no, I've never actually done any experiments. I've never used a laser, never used a computer. And he said, well, in that case, you will just have to work twice as hard, won't you? So that was the beginning of my transformation to an optical scientist. Now, single photon detection and counting distributions, one of the fundamental papers that launched that whole topic, as you can see over here, is Mandel's formula in the Proceedings of the Physical Society from Great Britain in 1958. And you see this formula over here. It is the formula that connects the ejection of photoelectrons with the incidence of a light field of amplitude E for a time capital T, which is the duration of the signal that is detected by the detector. And what Mandel was showing over here was that if you had a probability, energy probability distribution that was given by some function, then the distribution of photoelectrons, the number of photoelectrons K that would be counted in a time T would be related through this formula. And the intensity of the light could then be perhaps reconstructed through the photoelectron statistics. And so Mandel was really instrumental in launching the whole area of single photon detection and counting and so on. And this has influenced fields far and wide today, so that it's all over the scientific map now in different ways. Now, one of the very interesting questions that one encounters is the question of dead time. In this formula, the photodetector was assumed to have no dead time. What does dead time mean? Dead time literally means that after detecting a photon, the detector has a period of time during which it can't detect any other photons. It has to recover or recuperate before it can do that. And so since all photodetectors, photoelectric counting devices have dead times, Mandel in 1980 published a small 2-page paper where he talked about how does one take into account the dead time of a photodetector for a counting interval of capital T. If the dead time is tau, can one actually recover the ideal photoelectron counting distribution from the non-ideal dead time influenced counting distribution that one would measure if one operates a photodetector? So he came up with this very interesting inversion formula. And the way he proposed to actually implement this was not very easily done in 1980 when he published this paper. And so I'll transition to modern times. Here in Maryland, we have a system that actually detects photons and detects photons which are entangled. Here's the Aurea technology twin photon source, entangled photon source that we acquired around 2020 with photodetectors, which are avalanche photodiodes, not photomultiplier tubes. And these are the experts at Aurea Technology, whom I visited in 2019, just before the pandemic, shown over here in Besançon in France. And what we just did a study of, just was published a few months back, was to try and understand the counting of photons with dead time and how to correct for it using the Mandel formula. The Mandel formula from 1980 to achieve the ideal photoelectron distribution. And so one can actually do this experiment with a very simple setup. And this is an experiment done by Nicole Menkart at UMD with collaboration from Joe Hart, who is a scientist at the Naval Research Lab, and my colleague Tom Murphy over here in the Electrical Engineering Department. You see a 1550 nanometer distributed feedback laser. That's the wavelength of choice for optical communications, with an attenuation that is enough to make single photons incident on a single photon avalanche detector, and with the electronics, and then electronics for actually looking at the photon counting distributions and so on. So this is the setup that we just used. And just to make you aware of the problems of after pulsing and dead time that are often present in these detectors, you can see what happens when an electron arrives and creates a signal response, the SPAD response, single photon avalanche detector response, which is often looks like this, with a ringing curve that can often create problems because it can create false counts. This is the single electron, but if I did not know this, I would think there were two electrons that had come. That's the after pulsing effect. And the dead time effect is shown by the shading in gray over here. And if you have too short of a dead time, you will count these after pulses, which are spurious. If you have too long of a dead time, you will miss new photons that have ejected photoelectrons. And that is the problem with after pulsing and dead time that has to be dealt with when using these detectors to try to achieve good statistical distributions and knowledge of light sources. Okay, so here's the inter-arrival distributions with the 20 microsecond dead time. You can adjust the dead time in these Aurea detectors with the electronics. And if you look at the curves here, they are fit with a straight line on this log linear fit. And you can see that at the very end over here is a rising curve of events at very small inter-arrival times. And this is a sign of the after pulsing. So 20 microseconds dead time is not enough to take care or kill off the after pulsing effects. And you can see that when you use longer dead times, like in this case, we've chosen a 500 microsecond dead time, you do not have that steep climb at the beginning. We can actually get rid of that. So with a longer dead time, you can get rid of the after pulsing, but now you have to worry about the effect of the dead time on the photon distributions. And you may think that one of the ways that you can simply count or account for the measured count rate of photon arrivals in a counting interval t is just simply to replace the counting time by a compensation dependent on the dead time that is prevalent for your system. But oftentimes, this is not a sufficient correction algorithm that one can employ accurately. And I will show a few very simple results here. This is the raw measured in the blue shading, is the raw measured photoelectron distribution in time intervals of 150 milliseconds, how many photons arrived in those 150 milliseconds are shown here with the frequency distribution. And if I try to fit it with the mean of that frequency distribution, which lies somewhere right around there, I get a Poisson distribution shown by this black curve, which is way off from actually fitting this. So it looks like what I've actually measured is not a Poisson distribution at all. When one applies the Mendel formula, the iterative formula that Mendel came up with in 1980, and by the way, this was also derived around the same time by Mandyam Srinivas, who was at the University of Madras at that time and was a student of Emil Wolf. Mendel and Srinivas's dead time corrections, if you apply them, you actually see this beautiful fit of the dead time corrected Poisson distribution, and the waiting time distributions are perfectly exponential also. And you can see that with an attenuated laser, you get these very nice matches of Poisson distributions with the observed photon or photoelectron counts. Now we'll come back to this in a bit, but now I wanted to talk about optoelectronic communication for a little bit. So how does one send data when one actually tries to communicate with a laser diode that emits light? One usually uses an optical modulator to modulate the intensity of the light, transmit it through a fiber optic cable, and detect it. And you can use different kinds of photodetectors to sense the light. And this is the data that one will look at. Now, the data that one generates with this optical modulator is done by taking an electronic signal and modulating the light input into the modulator by creating a voltage difference on one arm of the modulator. This modulator, optical modulator, is called a Mach-Zehnder optical modulator, and the Mach-Zehnder interferometer is what is used in integrated optical form in this device. So the light coming in is split into two paths, the upper path and the lower path, and the lower path is changed in refractive index by the electrical voltage applied across the lithium niobate waveguide that is included over here. And the output of light depends on the voltage that's applied. So here is a detail of that. If the power input is P0, then the output power that one gets is given by this relationship in this optical light modulator applied voltage V that is shown over here. So as one varies the applied voltage V, one can change the transmission of light beautifully from a maximum to a minimum of pretty much extinguished light. And the voltage that's needed to do this is very small in these integrated optical light modulators. It's just a few volts, okay? So we wanted to experiment with these things. And right around 2004, I had a visitor in my lab at the University of Maryland, and this was a graduate student from Spain. So Jan Chambo was a graduate student with Pere Colette, who is shown over here, and he went on to be a postdoc with Laurent Larget in France afterwards, and then joined the CNRS later. But his topic of research with Pere was the theoretical analysis of what would happen if one, instead of detecting and just ending the open circuit that I showed on the previous slide, okay, if one actually turned it around and created a feedback system with a time delay and a nonlinearity in the optical modulator, that is shown over here is a feedback loop. So Jan and Hera and Laurent, those folks worked on this system, and they wanted to see the detailed dynamics of this system. And they used a very simple mathematical model of two cascaded single pole filters, very simple ordinary filters with a low pass and high pass characteristic that is characterized by these numbers tau and theta in this picture. And TD is the time delay in this loop, because we've changed notation a little bit here, but the cosine squared x plus phi function is the characteristic of the Mach-Zehnder modulator that's shown over here. And this simple equation was used by Jan Chambo and colleagues to characterize what was going on in this feedback loop. And this is a picture from 2010 in Cameroon, where we went for a hands-on school on complex systems. And Adam Cohen and Bhargava Ravuri are graduate students with me at that time at University of Maryland. And Shelby Wilson was a math graduate student at the University of Maryland, getting her PhD with Doron Levy on the growth of cancerous tumors. And Jan was working at CNRS at that time, and we are all pictured here. They are pictured here. I took the picture, I think, of these folks in Cameroon, in Buea, Cameroon. And these are our hands-on schools. The hands-on schools actually started in India. The first school was in 2008, and it was held in the Institute for Plasma Research. Abhijit Sen was instrumental in making it happen there. Harry Swinney and Ken Showalter and I are shown over here in this picture with the bulletin of the first school. And this is the school in Sao Paulo that was held with Adam Cohen, demonstrating the optoelectronic systems that we developed. This is me right here. And this is Bhargava Ravuri right here in Cameroon. We're doing our school there in Buea, okay? So now, optoelectronic chaos. What happens as we increase the laser power in that little feedback loop that we've created with the optoelectronic modulator, the laser light entering it, and the detector converting it to electrical signal, and so on. This is a simulation using that equation, that integral differential equation that I showed earlier, changing just the one parameter, beta, which is the strength of the feedback accounted for by that parameter. And it just depends linearly on the light power input, laser power. And this is experimental results which correspond more or less to what is going on in the simulations over there. Okay. So these were our early experiments on that. And then Tom Murphy created a very interesting system by introducing a digital signal processing board over here. And you can see that if you take bifurcation diagrams, you can compare them and start to notice all kinds of things from the measurements, such as the complexity of the system characterized by the Lyapunov dimension and so on. Now, these kinds of systems were actually practically used by a group in Europe in 2005, and the results were published here in this Nature paper by Apostolos Argyris and his colleagues. Claudio Mirasso was the leader of the European consortium, that Ingo Fischer was involved in the experiments, Pere Colette, various people. You see Stefano Boccoletti along with Claudio in this picture in Mexico. But this experiment was done to try and transmit data using just the feedback system that I showed you earlier, and transmit it on a real fiber optic communication network in the city of Athens, Greece. And here is an example of synchronization between transmitter and receiver that was quite accurate across a lot of kilometers of fiber in this optical fiber link system that was present in Athens. And when they looked at the message that was transmitted by doing the suitable decoding at the receiver end, they were able to recover the bits sent pretty accurately at about a gigabit per second. Now you see over here a book on optical communication with chaotic lasers written by Atsushi Uchida. And by the time the book was written, people had done 10 gigabits per second. And just a few years ago, here's one example of 30 gigabits per second over 100 kilometers of fiber. That was done in Shanghai not long ago. Okay, can we make larger networks of coupled nonlinear oscillators, of these feedback oscillators? Here's Caitlin Williams, who built 4 of these on an optical table in our laboratory at the University of Maryland. She is now in the fiber optic sensors division at Naval Research Lab. And with these kinds of systems, just 4 of them took up the whole optical table. So one had to think a little bit harder about how to create lots of synchronized oscillators. And as you can see, there are many different kinds of synchronized oscillators one can work with. The synchronization of 2 candles from the Ikiguchi lab. Let me see if I can turn this on. The video is not coming on for some reason, though it seems to be working. I am sorry about that. But here's an example. You have actually seen candles oscillating together in Sujit's lab as well. And here's a paper with William and Sujit and co-workers. Description. For some reason the videos are not playing, but so I will not try to do this anymore. Let's go over to the next. Oh, that video played. It's very interesting. Some of the videos didn't play, but this video was actually playing. This was a video on let's see if I can make it happen. The Millennium Bridge disaster, which all of you might have heard about. This was a paper that came out in 2005 by Strogatz, Danny Abrams, Alan McRory, Bruno Eckhart, and Ed Odd. Bruno was a visitor at the University of Ireland at that time. Another connection with Germany. And here's Ed Odd and Steve and Bruno shown in this picture, and you can see the synchronous behavior of the pedestrians on the London Millennium Bridge. Well, motivated by this this phenomenon, I started to look at a project with a visiting Spanish graduate student, Jordi Zamora-Montt, who was doing his PhD with Cristina Massaler and Jordi Garcia-Ojalto. And you can see we did something on critical transitions in complex systems in a certain sense, crowd synchrony and quorum sensing, and we predicted a first-order phase transition-like behavior in a whole array of lasers that were coupled through a hub laser. We didn't have the wherewithal to actually do the experiments at that time, The experiments were done 10 years later in near Davidson's lab in the Weizmann Institute and came out a couple of years ago. And you can see that they were showing the effect that you needed a certain quorum to actually make the lasers synchronize. And this agreed very, very well with the predictions that we had made in the paper in 2010. So let's now come on to something more recent. Single photons and quantum random number generators, the last topic, a few minutes. And photon counting has always been a very interesting way to generate random numbers. Here's a commercial device made by a company called Pico Quantum, Switzerland. And they look at the photon arrivals and create random numbers from those. So this is the paper in which this is described. I will not go into the details here, but note that physical random number generation by systems of this kind are very important because they can be very fast if one wants to use fast physical systems. And I want to show you a result from Atsushi Uchiwa's lab, alongside others, recommendations and illustrations for the evaluation of photonic random number generators. It's a review article with new results as well that we wrote. Joe Hart was the architect of this paper, and we collaborated with Atsushi and his student and with other folks here in Maryland. And using lasers, they could generate light with a spectrum of over 40 gigahertz. And when one did that, one had a way of generating random numbers at very, very high speeds. So this was one of the highest speeds of random number generation. And there are lots of interesting anecdotes and details. I suggest that you might want to look at this paper if you want to see some of the details. But there are many different methods of trying to generate random numbers, and there are certain limits. One is the Shannon-Hartley limit, which is very important to observe and understand. And in our own lab in 2015, Aaron Halverstrom utilized a photon counting detector in the feedback loop configuration that I showed you, and did a beautiful experiment to look at the arrivals of photons and try to understand what happens as we increase the number of photons incident in one round trip time, one delay time. As we increase the number of photons incident, does one actually get something interesting happening in terms of complexity? So Aaron is shown here counting photons in this covered up little apparatus. It's a very simple apparatus shown in the previous slide. And what he noticed was that when you just had a few photons per round trip time, the delay time, 12.5 photons on the average, you got Poisson statistics out of the system. And as you increased the number of photons incident in the round trip time to about 200 photons, you started to see deviations from Poisson and the buildup of many further features. And as you went to higher and higher numbers, you started to see things that could be reproduced rather well by deterministic simulations of the equations that he was working with. So you see Poincaré sections over here of the low photon number limit, where everything is stochastic, going over to the high photon number limit, where you see the birth of a chaotic attractor take place. So I hope you can see this 3 dimensional embedding of the photons arriving at the detector, going higher in the number of photons, and developing from what looked like a total blob of Poisson statistical arrivals to an attractor that's totally reconstructed from experimental data and which now shows a distinct shape of the attractor in this three-dimensional projection. Okay, so I think my time is pretty much up, and I want to summarize by saying, yes, detection of light can be done by photochemical means with our eyes, with photoelectric, semiconductor, avalanche photodiodes. We can detect single photons. And this is all very interesting with many different kinds of applications. Optoelectronic oscillators can be built. And there are many applications of these kinds of systems. And I won't go into the details of some of the more recent ones that we are currently exploring in our lab. But I want to mention that these two groups of research goals, how does this transition from quantum to classical dynamics, quantum to classical deterministic chaotic dynamics in particular take place? I've been influenced by many significant people in my life, Len Manel, Emma Wolf, Joe Ford, Ron Fox. You see their prints on the work that I have tried to demonstrate. And here is the second topic on networks. I have been deeply inspired by Yoshiki Kuramoto, Steve Strogatz, Ed Ott, Lou Pecora, various people, Jürgen Kurtz, and in my life there have been many transitions from one topic to another, but these two themes carry through all the way. Thank you so much for this time, and I will be happy to try to answer any questions that may appear.
Yes, thank you very much, Raj, for the really great and so inspiring talk. Let me add only one little historic thing, because Helmholtz was born in Potsdam. And we are, of course, very proud about it. It's another stronger bridge. Okay. And by the
That's
way,
a wonderful connection to bring in.
Around the corner there, I lived in Potsdam. Okay, good.
That's
but now
fantastic.
Real questions, please. Who has questions? Are there questions? All is clear? No, impossible.
I don't have to worry.
There is. Sir, can you elaborate on how? Right. Can you
Shall
elaborate?
I stop sharing?
On how a laser pulse could be reduced to a single photon pulse using an attenuator? Is it that easy to optimize?
So a laser, this is not a pulsed laser. This is a continuous laser. And you can reduce, pulsed lasers as well by attenuation. But the laser that I was showing was a continuous wave laser. And we need an attenuation of roughly 140 decibels, okay, to reduce the milliwatt, 100 microwatt level of light down to the level where just single photons are incident on the counting time interval that we were talking about. So those kinds of attenuators are now available in fiber optic systems. And there are many commercial makers of such attenuators. And we just actually purchased these attenuators and stacked them together to produce a level of light that would correspond to just single photons or few photons incident on the time intervals that we were counting over. it is quite routine to be able to do that. What we did was stack fixed attenuators first, and then at the last stage, we had a variable attenuator that could be varied to change the light intensity over a range of about 1,000. And so it is quite possible to do that with these lasers.
Hello.
Hi.
Thank you for a
Yes.
wonderful talk. I was fascinated by your statement about our eye to detect single photons. So I recently heard about two historical statements about it.
Yes.
The first is apparently C.V. Raman,
Yes.
while doing experiments in his dark room, after he switched off the light and so on, he saw some
Yes.
flashes of light, even though there was no light in his eyes. So he then counted the number of leaking photons. So he made a speculation that our eyes are able to detect single photons. This is recorded
Yes.
somewhere in writing. I don't have the reference right now.
So very interesting comment. Thank you so much for making that comment. So what I had heard was that K.S. Krishnan, who was Raman's student at that time, used to do his experiments on trying to observe the Raman effect after completely dark adapting his eyes. He was very meticulous as an experimentalist, and Raman too. And these people would adapt their eyes to the dark, and they would then try to do the experiment so that they could detect the faintest of spectral lines using this method. I would be very interested to see any references that you may be able to send me on C.V. Raman's conjecture.
Yes,
about
it's there in my computer. I will
detection.
find out and
Yeah, I would be very
Then
thankful if you
one
could
more
show me.
historical comment. I read recently that apparently Lawrence, the famous Lawrence, he was looking to some experimental study of our eye perception of the eye when the intensity of the light is decreased. The experimentalist found that at some point the perception stopped discretely, and Lawrence estimated the number of photons. He counted it to be about 10. So he came to the conclusion that we could count up to 10 or 20 photons. This is also something I recently heard.
That's very interesting. So I can, I'll be delighted to give you the link. Okay, I would love to see that. And this recent paper that I mentioned from 2016 on the human eye direct detection of single photons may have references to that as well. I will check that out.
Sure,
Thank you so much. Yeah, thank you.
Further questions, please.
Yeah, Professor Roy, how large a network of lasers you can design in your lab, and what is the present status?
So the present status of my lab, Professor Lakshmanan, is that I have transferred my lab completely to Professor Thomas Murphy. So, so in fact, I have, in many ways, I am trying to figure out a transition, a critical transition in my life at this point of, but to answer your question more seriously, the kinds of network size that we could create, we were limited, as you could see, with the fiber optic networks that we were talking about, to just a few. And as fate would have it, at that point, we were using first, to create large networks, we were using liquid crystal spatial light modulators. These were spatial light modulators with several hundred by several hundred pixels. So several thousand possible pixels, but we would often group the pixels together to create smaller ensembles. And typically, the spatial light modulators could create about a few hundred or several hundred coupled optoelectronic systems in these feedback loops using the spatial light modulator liquid crystal systems that we were operating. Our spatial light modulators broke down some years ago. At that point, we decided we had to think of a smarter way of doing this, because spatial light modulators cost us about $25,000 each, and they lasted maybe 10 years, but not more. So Joe Hart discovered a beautiful way of creating networks using a combination of a single light modulator system with a field programmable gate array. And this we published around 2016. And with that, we are able to create several hundred to 1,000 or thereabouts dynamical nodes in a typical setup. That may be extended further. Joe is actually working on these systems at the Naval Research Lab with very state-of-the-art field programmable gate arrays and modulators. And he may well be able to extend this beyond what we were able to do a few years ago. So yes, it's up in the thousands, but that's being, that's
so you are able to identify
yeah.
chimeras and
yes
kind of
yes. With systems of several hundred, we could really do experiments with chimeras using the spatial light modulators that we first employed, and subsequently with these FPGA based systems. Yes.
Okay, thank you very much.
Welcome. Yeah.
Okay, so the next question is from, can you hear me? From Prashant Singh.
Okay.
What was the cost to occur for the attractor when the number of photons was enhanced? It seems like nucleation around which photons start to oscillate. I think he's wanting your comment on this observation.
So his, could you just repeat the beginning of his question?
What was the cost for the what is the cost of occurrence of the attractor as you increase the number of photons?
What was the cause of the occurrence of the attractor? So the attractor is occurring as a result of this feedback loop. There are two major ingredients. One is the nonlinearity of the optical modulator, and the other is the time delay of the feedback loop. The time delay can be adjusted using our digital signal processing boards. The modulator nonlinearity is pretty much fixed to this cosine squared nonlinearity that is a characteristic of the integrated optical material, the nonlinear optical material that we're using. So those are the causes of the chaotic attractor. But the chaotic attractor doesn't actually form or have birth before enough number of photons start to arrive during one round trip time delay. And that is what I was trying to show using that video clip right at the end. Thank you for the question. Yeah.
There is a follow-up question.
Yes.
What's the kind of attractive interaction with photons in the presence of unstable equilibrium state?
I am sorry, I'm not clear about the question.
Yeah,
could you repeat that?
I didn't myself understand it very well.
No.
The kind of attractive interaction within photons.
Oh, there is no interaction between photons in this system, even when they are arriving at fairly fast incidence. The photons are not really interacting with each other in any way. It is, the system is quite fast enough in its electronic response to take care of that. And that's why we limited ourselves to a few thousand photons over the delay time. So there is really no interaction, in a sense, between the photons. They are single photon arrivals which are counted separately.
Okay, thank you. I do not see any other questions in the chat box or Q&A. Would any of the...
I see a hand raised.
Yeah.
Hello. Yeah, very nice talk. And I really like the historical part introduced. So one question is regarding your earlier, just a comment before this. What would you call that bifurcation, where you have periodicity to chaos happening in this feedback loop? What's the nature of the bifurcation from a dynamics point of view?
That I do not know that I have a simple answer to your question, but the bifurcation is from the periodic oscillations to chaos, and the best place I can recommend to look it up is in the papers by Jan Chembo in around 2005-06, around that time. The reference was in my talk, but I can send you the paper.
Okay.
Okay. Yeah, I'll be delighted to send you the paper. He tried to do the bifurcation analysis in his PhD thesis, particularly. And I don't know of the exact, I don't remember the exact route to chaos in detail, but it is from a half bifurcation that one starts.
It's very different from the normal types. That's what I was wondering.
Mm-hmm.
Okay.
Thank you.
Yeah, I'll send you the references, Ambika.
Okay, thank you.
Yeah, I think we are out of questions. So I just have remark that your questions 1 and 2, those are the questions that we also try to address, but more in the context of thermoacoustic system, which are like acoustic lasers actually. So we have been following your work, and I mean, there seems to be a lot to learn from you. And
yes, I think these are questions that attract lots of people because of their universality and their spread across disciplines, as you pointed out, Sujit. I think this is a marvelous feature of these kinds of questions. And it's so wonderful to see how you are taking it in the field of thermoacoustics and detection in combustion systems. So
one more question has come up. Are there studies where photon transfer occurs between pulses?
Between pulses, okay, but this is not a pulsed laser, so I'm not sure I can answer that. The systems I was working with are continuous wave lasers, and it is the feedback that is actually shaping the dynamics. But if you are talking about the pulses of the single photons that are being detected, there is no interaction between those detection events. So in other words, in that video that I tried to show you, we try to keep the dead time effects to a minimum. We try not to let the dead time effects come into play. And that's the regime we're utilizing for that video. Unlike the cases where I showed you earlier, where the dead time effects play a hugely significant role in determining the statistics.
Okay, so I think we are done with the questions. So I want to take this opportunity to thank you for accepting our invitations and giving this very nice talk with a lot of historical anecdotes and references. It was really inspiring, and thank you so much.
Thank you so much. And I love the connection with Potsdam through Helmholtz that Jürgen brought up right at the end. That was a wonderful way to reconnect with the feedback loop.
We'll see everybody after New Year. I will send announcements in some time. Thank you all. Have a nice evening.
Thank you so much. It was wonderful to be here and talk to you all.
Nice meeting you
and see
again.
Very good to see you all. Bye.
Thank you. Goodbye.
Bye-bye.
Thank you. Bye-bye.